Okay, so just before we turn it over to Professor Edgar, let me just say a few words about him. He received his Bachelor of Science from the University of Kansas, his PhD from Princeton University. He's concentrated his academic work in process modeling, control, and optimization, and he's authored over 500 articles and book chapters. He's the author, one of several authors of a popular process control book that I use as I teach process control, but he's also done several other things. In 1997, he was the president of the American Institute of Chemical Engineers, and he was also the co-founder of the Smart Manufacturing Leadership Coalition, and he was previously the director of the UT Energy Institute. He's a member of the National Academy of Engineering as well. So with that, let's go ahead and welcome Professor Edgar and turn it over to him for his technical lecture.
Can you hear me in the back of the room? Okay, we'll just go with this. Hopefully there's not going to be any interference here. So John actually left out the fact he was also my PhD student in 2004, 5, when was it? 2004, graduated in 2004, and then ended up here at BYU. And of course he was an undergrad here as well. So this talk is going to follow on the one I gave yesterday. Yesterday was a more general talk, largely around power grids and carbon emissions, and you'll see some of those things come back today, but again, it's going to be a little more specific around, as you'll see, around thermal storage and solar energy. But I'm still going to try to give you some kind of overview about different things that are happening that are relevant here. Again, I want to thank Reed Izatt for being the sponsor of this nice lectureship, and I've enjoyed getting to know him while I've been here in Provo. So, I didn't ask about, I think I can just advance this thing this way. Okay, so we're going to be talking about, yesterday we were talking more about carbon emissions and, trying to figure out ways to get carbon out of the power plants that are out there in the world and in the U.S. But of course, that's just a surrogate for energy efficiency. And so today we'll probably not talk so much about carbon emissions, although that's certainly, we still like to strive for high efficiency when we burn a fossil fuel. But a lot of what we'll be talking about today will be about using solar. And that'll be one part of it. So using renewables, but again, there's some clever things we can do with old technology, which is just thermal storage, that can gain us lots of benefits, and I'll try to explain again why that's true. And as you see also, there is going to be a component of that, which is one of my main research interests, which is using process control in order to actually get better results in terms of efficiency. Okay, so we'll start off with a little bit of overview and talk a little bit about maybe energy conservation, and then talk about some of the different power production alternatives and why we're trying to figure out how to run a power plant, why it's a dynamic problem to begin with, and we're going to be interested in saying, okay, how does that fit with smart grids, and how do we use two other dynamic things, namely energy storage and process control, in order to get better results overall in terms of financial results, carbon emissions, energy efficiency, and so on. But we'll start with really kind of a broad view of energy efficiency. So back in 2001, we had a vice president. Some of you may not remember these guys, especially if you're undergraduate students, Dick Cheney, who basically came out in 2001. He was the vice president, but he was put in charge of energy policy because he was an oil and gas man, so he knew energy, right? So he basically said that, we don't need conservation, okay? We should just, figure out how to get more oil and gas and start, increasing things. Because again, at that time, the energy requirements are still going up like 5 or 6% a year. So it was, and you start doing that over a 20-year horizon, you get some pretty scary numbers in terms of what you're going to need. But he decided to slam conservation by saying it's not a sufficient basis all by itself for a sound, comprehensive energy policy. Okay, so we're going to object to that now, 20 years later. And he said the government should not step in and force Americans to use less energy. Okay, well, you can say there are going to be requirements. We like to encourage people to use less energy, and we like to kind of have that become a mindset in terms of how they operate and how they live. So hopefully, if you just are at the point of saying, yeah, I just finished drinking a Diet Coke and I put the can in the recycling, right? Well, that's a good first step, but we've got a long ways to go from there. So I like to say this is like our choice between megawatts and negawatts, okay? Negawatts being we're not going to use that energy, right? So we like to figure out ways to do that. In general, whether we're talking about some of these energy systems, big energy systems we're going to operate, but also I think since I believe this is a university that believes in personal values, so we'll talk about personal values here too, okay? So if you think about, the kind of things we could do, you as if you're in your own home, about things you can try to do to use less energy, we can have better, more efficient refrigerators. So how many people have bought a refrigerator with lower energy consumption? Few people have. Maybe the students have not had to buy a refrigerator yet, but the point is that refrigerators today are essentially 3 times as efficient as what they were 30 years ago. How did that happen? Well, it's because, first of all, maybe the manufacturers thought it'd be a good thing to do, but then we had a lot of people, including government regulatory bodies, saying, let's have something called Energy Star appliances that are more efficient. Let's try to go that direction. And so, we could do that. You can have more efficient dishwashers. You can have more efficient washing machines, or have a front-loading washing machine. You could think about your hot water heater just sitting there heating up all the time and losing heat to the environment. Maybe we need tankless hot water heaters. Light bulbs have been, certainly contentious for a lot of reasons. Making that changeover from incandescent bulbs to essentially fluorescent bulbs to LEDs. And again, with successive great reductions in the amount of energy, because incandescent bulbs are really great for heating your rooms. Lighting-wise, they're not nearly as great, but of course we got used to having those kind of bulbs, so we like them, we hate to give them up. Now, we don't have to do that. The current administration saying, no, we don't need to do light bulbs anymore, we should go backwards on that one. Well, again, there's a lot of things happening today at the government level that seem to be reversing our attempts to try to become more efficient, but because they just don't like the idea, or it's a pain to do or something. So you could put in a digital thermostat, have a programmable in order to manage the amount of time your heating system is operating or your air conditioning system is operating. And of course, being able to access that through, say, a smart thermostat or your smartphone gives you even more ability to do that. Shade trees are also a good thing. You can reduce, energy use that way. So these are all things that you as someone who has a home or an apartment or a condo or whatever, you can do all these things and contribute, I think. So here's one of my few jokes today. I showed more of them yesterday. So this is like, someone who wants to be more green. Here we have Dilbert, and he's walking around in his underwear, as you see up there, the top panel on the left side there. It says, "Don't be frightened by my green clothing." It says, "I'm going to be working at home today," so he's telecommuting. He's not using up creating carbon emissions. And he says, "But my telepresence meetings will only display me from the chest up." So no one knows that he's walking around that way. And of course, he can reduce the amount of material in his garment, so he uses less soap and water. So okay, less laundry. And then finally he says, "But I also get more freedom of movement in this fewer clothes because I can mouse more efficiently." Okay, so we can all create our reasons why we want to do this, but he had this particular thing that he wanted to do. So a number of years ago, Al Gore came out with this I think really impactful movie called An Inconvenient Truth that really riveted people's attention on where things were going with climate change. And we've gone, there's been lots of debates about climate change, even continuing today. But as part of that movie, basically said we can do a lot better if we do certain things in order to reduce energy consumption in the U.S. So if you remember what I said yesterday, that the U.S. has been using roughly about 100 quadrillion BTUs per year for the last probably 10, 20 years. This was actually 2006 roughly was when that came out. So he said, can we go heavily into mass transit? Well, obviously that's only seems to be working in a few places. but you could save 1/5 of the total energy consumption, okay? And then you just go down the list here. I don't need to enumerate everything here. You can look at it. You can see, okay, more insulation, good thing. You know, green building would be another area that you could, you know, improve things a lot. Efficient lighting, heating, cooling, appliances, as I mentioned already, telecommuting, that's 1 out of 100, and so on. So 40%, this says, of the energy consumption, we could find, you know, ways in which we could reduce it. So if our goal was just go strictly conservation, then that's fine. But of course, I don't think we're willing to do all these things, or maybe it just doesn't fit. You know, if you said, I mean, I know there's a reasonably successful light rail that runs in Utah, but again, we're not going to replace all the cars and trucks that are driving around, you know, Salt Lake City or Provo or wherever with this kind of approach. So I think we have to still think about, we have to come up with more energy, but when we have a chance to save energy, I think we ought to do that. So a number of people have done studies about, you know, how can we become more efficient. So if you add up like industrial energy usage and buildings are a big deal too, that the buildings like, you know, this one we're in right now. By the way, I forgot that I know people put in $1 when they came in today because that's the price of admission for this theater, I understand. We didn't collect that. Oh, sorry about that. But in any event, you know, commercial and residential are about 50-50 of the building energy consumption. And so there's a whole lot there. And of course, transportation is going to be the rest of it, most of the rest of it. So again, there's lots of areas we can focus on in here, but industry and buildings can apply to, it's like 70% of total greenhouse gas emissions. So that should be a big target for us, right? We should look at that and figure out ways to do that. You know, we're going to continue to need electrical capacity, but a number of, you know, people with good reputations have said, you know, we can, you know, reduce essentially the energy use in buildings and industry by 25% in the next, well, now 10 years. So this was actually, I think they made this statement 5 years ago. So again, these are all big targets that I think are worth working towards. You know, one of the reasons that the whole energy business is complicated, and I talked about this a little bit yesterday, and there's a little bit of a graph that maybe helps you understand, you know, things are always changing. And so if you look at this, let's see if this is working here. So we're just looking at 3 fuels here. This is a lot less complicated than some of the other graphs I showed yesterday. But you can see that, you know, we've had these periods, you know, this is like during the first Arab oil embargo. So we went from, and these are now in prices, dollars per million BTUs. So I'm not using metric here. I'm using, you know, what most people use in the industry. So you can see the price went way up during the Arab oil embargo from 4 to 10, almost a multiple of 2.5. And then it comes back down again at the end of the Arab embargo, and we kind of slump along here. And then all of a sudden we start getting, you know, we're short of oil and gas again. The price starts going up again for this. And then you see also natural gas. Here's the orange line here. Again, some variations, but you can see that even in 2010, the price of natural gas was like 3 times what it is today. So now we're down around $2 per million BTUs if you go beyond 2015. So again, depending on when you look at these problems, you maybe come up with different conclusions about, okay, well, energy prices are now a lot higher, so it becomes much more of an incentive to worry about energy efficiency. Now that we're down at lower levels, maybe not so much, but again, I think, and then finally, coal you can see is actually the most stable price, this blue line here. And so again, it's down around $2. So you can see that, you know, right now the price in terms of just the price of the fuel for coal and natural gas are basically the same. Okay, I'm not going to talk about oil in this lecture because that's really, again, pretty much the transportation side. I'm not going to really talk about that. And of course, as many of you know, that there's been this thing called shale gas that has developed in this country that's really allowed the U.S. to become you know, more self-sufficient in terms of its energy requirements. The price is low. It's, you know, people figured out with fracking, you know, how to get access to it, lateral drilling and so on. You know, a lot of improvements technologically in order to achieve that. You know, we're starting to now see that natural gas is a preferred fuel, say, over coal for uses power plants. And I talked again a fair amount about that, and I'll come back to that in a little bit today as well. And just remind you again what the differences are. Of course, if the price is the same between coal and natural gas in terms of the price per million BTUs, then you start thinking about, well, okay, what's involved with dealing with coal in say if you're burning it compared to burning natural gas? Well, you know, in coal you've got essentially lots of environmental issues. You've got essentially sulfur, you've got nitrogen, you've got particulate matter, you've got mercury, you've got a whole lot of things you have to treat in order to make it environmentally acceptable. Natural gas is viewed as a clean fuel. It's not green, but it's clean. It doesn't have to have all the pollution requirements that we would have for coal. So obviously coal becomes, you know, relatively more expensive. But then there's also an efficiency argument that one can make for natural gas, which I'll get into in a minute, which is we can achieve much higher efficiencies with natural gas and using more advanced power cycles, not just traditional steam turbine combustion. And of course, the other part of the nice about the shale gas revolution is that it's not just confined to Texas and Louisiana, which is where a lot of the oil and gas development has historically been, but rather it's in the Midwest, it's in North Dakota, it's in Pennsylvania, and so on. So there's a lot more places where they can be doing this, and of course that gives you the ability to now do commercial development, new plants and so on in other parts of the country, although there's still plenty of it going on in Texas. Since I live in Austin, I'm quite aware of that. Okay, just again a simple kind of comparison between conventional efficiency for a power plant, and if you're using the old style power plant, you're down around 30% efficiency. If we start now worrying about using combined cycle or type of power plant, and again, this is really illustrated. I don't have time to really go through all the details here, but just point out to you that you know, we can get, you know, over 50% efficiency with combined cycle today. So that is immediate improvement. The other part on the carbon emission side is that we're dealing with CH4. So a lot of the energetic content basically is coming from hydrogen, which makes water when you burn it. So the carbon emissions are down even for even additional reasons. But then if I can somehow combine this with industry who might need steam power, then I can improve, instead of having a 49% efficiency here, okay, that by having essentially combined heat and power, or CHP, then I get up to 75%. Now, I made the mistake one time of saying, well, that means that natural gas is nearly renewable. Well, some people didn't like making that conclusion, but I'm just saying it is. It's moving in the right direction, okay? That's at least a good sign. And, you know, once you get up, and I'll be actually talking about systems today, power plants like the power plant at my university, University of Texas, where we're even better than this, okay? We're up over 80+%. So those are all, I think, you know, definitely things that we need to be moving towards. Well, one of the other things that's happened is smart grids as a way of essentially trying to be more efficient in terms of, you know, how we operate power plants, but also in terms of how we interact with the consumers of power. And so instead of everything being one way, where you basically, you know, produce power and then basically someone plugs, you know, their hairdryer into the wall and basically, you know, gets power. Well, that's one-way power. That's historically the way, you know, we've always done it in the power business. But now we're starting to see, you know, improved communication, control, and essentially interaction between the utility and customers, and you know, try to do things like variable pricing of power during the day. And I'll explain to you why that turns out to be something we might want to consider. But then also, smart grids will allow us to start bringing in other kinds of energy sources like solar and wind, which are renewable, but it also does increase the need for energy storage. So this is, again, something I showed yesterday, but I want to talk about it again, which is that you see that coal and nuclear here, and this is actually a snapshot from a summer day in Texas. So you can see that, you know, here's nuclear down here. It's pretty much flat, okay? Base load type power generation. Here's coal. It does vary a little bit during the day, but again, you don't turn coal plants off and on in order to respond to demand. Here you see wind coming into play. So it's being, you know, a little bit of wind here. This was, you know, this looks like it's about, I don't know, 12% or 10%, but now in Texas, for example, ERCOT is the grid Electrical Reliability Council of Texas, basically this is up to like 20%. But then our swing fuel is natural gas. Okay, so you can see that obviously during the day, people come in, you start, having energy needs when people wake up in their home as they go to their buildings, their offices, or factories, or whatever, and it starts rising, and then basically, and this is again on a summer day, it hits a peak somewhere around 4 o'clock in the afternoon, and so you start thinking about, well, what does that mean cost-wise? Well, this is what we call, in the past, we call this peaking power, okay, because we're trying to hit this peak, and of course, when people come home from the office, and then they set their thermostat, during the day while they're out of the home to, something like 82 degrees or 80 degrees. They come home and they say, oh, okay, let's pop this thing down to 74. Well, if everyone is doing it at that time, then we get this peak. Okay, that's going to cause a peak power consumption, and that can cause problems with the grid because all of a sudden everyone's trying to draw power, and the power plants have to respond to that. So in any event, the other part of this I want to point out to you, though, is that because you're not running, as you increase this, if I could have like one or two baseload natural gas plants, then I could have, natural gas basically running constant here, but I still have to have these peaking turbines coming into play. And so these turbines may only be operated like 10% of the time, okay, just enough time to deal with the peak. And so when you start thinking about, since you're mostly engineers here, think about, investment analysis and, what's, discounted cash flow or net present value, that if now I'm only operating, 20 days a year or 30 days a year, or the equivalent number of hours, as opposed to something that runs 24 hours a day, 7 days a week, 365 days a year, then the relative capital cost for these peaking systems are going to be a lot higher. So we've got to find ways to flatten this peak so that we're not, having to spend so much money on this expensive power. The other thing I'll point out to you also is that if you look at this, you can see, well, hey, that kind of looks like what we think solar energy might be doing, okay? In other words, sun comes up here, we get maximum radiation and ability to collect energy from the sun, whether it's thermal or photovoltaic. But the point is that it hits a peak sometime in the mid-afternoon, and then it starts declining again, okay? So we don't have that available to us at night, so that's a problem with solar that we have to worry about. Now you might say, well, yeah, wind is going to help, isn't it? And I showed you part of that slice that shows wind. Well, the problem with wind, at least in Texas and probably a lot of other places, is that the wind blows more at night than it does during the day. Okay, so if you look at this is actually a kind of a normalized curve, but basically you can see again, here's that demand curve we talked about. Okay, peaks again at 16 hours, okay, 4 o'clock. But here's what wind is doing during that same time frame. So it's actually highest here at night, 3 a.m., late in the evening at 10 or 11 p.m. But then you can see it's dropping off, and then comes back up again. So the wind is not going to help us much for the peak power problem. Now, having said that, though, that I mentioned that now Texas is like 20% wind energy, which is the highest in the country, and it also, as someone said, it would make Texas the 5th largest wind-producing country. So we sometimes think of Texas being separate from the U.S., but anyway. So, it's a big deal, okay, and it's happened, remarkably well. But it is, remember, it's dynamic. So is the wind blowing? Is it not blowing? It's changing. How do you manage all that? So and there's a whole bunch of people who work on just that whole aspect of how we make wind work. Now, I'm going to not talk much about wind here, but talk more about solar today. So again, if we kind of represent what's happening in the grid, then this is like the one-way idea, and then we get to basically, and so we've got a number of different consumers, offices, factories, houses, hospital, apartments, and so on. And then we could have, again, wind power, solar power, et cetera. These days, actually, what's happening in Texas anyway, I mean, you could say, yeah, let's let's put up solar panels on a roof, like what Reed has done. He was showing us that last night. I don't. People here may not remember, but back in the 80s and 90s, people were actually doing hot water heating on their roof, and that's still going on in a lot of countries like Israel and other places around the world where they get a lot of sun. So, but now we're and then solar is actually, instead of people putting PV panels on their roof as the main way in which solar is collected, the most of the action in Texas with solar right now is really with solar farms. So in other words, you basically have gigantic areas that are going to be devoted just to solar panels, and then you have to have capability of transmission from, in this case, West Texas to Central Texas or North Texas, where all the people are. But the point is that turns out to be really cheap. So if you remember anything about your charge on your bill, the retail charge may be something like 10 cents a kilowatt hour or something like that, and maybe the cost of actually producing that power, forgetting about the retail side, it was like 6 cents per kilowatt hour. So now the bids on solar farms are coming in at 2 cents per kilowatt hour. So there's a big incentive to, if you're going to build these things, build them bigger. And right now, if you look at the planned additions to the grid in Texas, it's mostly solar and not wind. So we're kind of hitting the end of the wind part, but solar is now going to start becoming a bigger thing. Okay, so again, highlight those other options on the power station. So that's, those are new things, relatively speaking. And then, some people might refer to this as Smart Grid 1.0, but then now we start saying, let's even think further out, and it's going to be Smart Grid 2.0. And you can see there are a lot more things happening now. If we draw this diagram, we're going to have energy storage potentially at different places along the way. And so these are maybe green buildings. They may have, again, solar panels on the roof or out nearby. We might have plug-in hybrid vehicles that are going to need power in order to charge also at night, right? So they have to be involved somehow. We may have other things around how we manage the energy in any of these buildings. So how we do this, of course, is lots of different things are going to make this the next grid even different. And again, there's going to be increased amount of computational intelligence that's going to be required to operate this system. Okay, so I mentioned to you that we'd like to reduce the peak, and so what utilities have done actually for a number of years in various places have said, well, if it is going to cost me more to produce power in the afternoon, then let me just charge more for that. Okay, so let's have a different charge for that. And there's different ways that you can structure the pricing. One's just called time of use. Another one might be a critical peak pricing, and I'll show you a graph of this in a minute of what might be typical. Or there might be rebates that you give to the consumer. Someone yesterday was talking about having the utility can actually control your thermostat, so that's another thing that happens. There can also be something called real-time pricing, which means that in a sense instantaneously there might be a different price that you don't know what's going to be ahead of time. And some people don't like that because they don't know it could go up by a factor of 10. And when that happens, you might want to turn everything off. I don't know. But the point is it can be changing. So this might be a typical pricing pattern. This was actually from, I think, the Chicago area. And you can see again in the fall, winter, spring, when demand's lower and there's not air conditioning issues that you're worried about, you can see what that looks like. It went up, and these are again old prices, but again it's representative. 2 cents up to 6 cents, and then again at night it goes back down to 2 cents. There's some utilities that are in the retail market in Texas where they say, we give you free power on the weekends. So again, they're all trying to figure out ways to entice people to become users of their retail plan. So there's lots of things you can do. But then look at summer here. Again, low price at night, then it spikes up to 11 cents in this case at the peak time, and then goes back down again. So this is another way in which utilities can try to push down that peak. And that's though without any energy storage and so on. I'll show you about what we can do with energy storage. And I might mention all for those, since you're pretty much all chemical engineers, is that the interesting idea about smart grids has actually been around in the chemical industry since the 1970s. Okay, so this is actually a diagram that's it's out of my optimization book, but basically, you're basically running an energy system in every major plant in the Gulf Coast, for example. You're going to make high pressure steam here, and then basically you're going to have different levels of steam. Medium pressure steam, MPS, high pressure steam, depending again where in the plant you're trying to access steam and what levels of steam you need. You're going to have let-down turbines that basically can extract energy as the steam goes from, say, high pressure to medium pressure, or medium pressure to low pressure, and so on. And then over here on the right-hand side, we've got the ability to say, okay, I can either buy power from the utility, or I can produce power and then send it out to the utility. And so Reed was actually showing me and John last night a diagram of how he's producing power from his solar panels netwise on his house. So this idea has actually been around a long time of, and of course what happens in cities like Houston in the Ship Channel is that again, they're figuring out if the price of energy is a lot higher during the afternoon, then I ought to be making more power then because it's cheaper as opposed to buying it. And then at night, maybe you take more power back again. And so you can, again, move these plants around a little bit dynamically. Okay, so if we have a strategy on how we reduce carbon emissions from the grid, here's a number of things that I think we can think about. I talked yesterday a lot about reducing use of fossil fuels. And again, if you watch any of the Democratic debate the other night, several cans were saying, we need to eliminate fossil fuels. Well, I don't think that's a practical solution, but it's a nice idea, I guess, more than anything else at this point, but not something we can do right away. But then we can talk about how we increase use of renewables. But again, that comes with the price, which is renewables are intermittent, so I've got to worry about the dynamic nature of that. But since I've already pointed out to you that the grid is also dynamic, so now we're trying to match up one dynamic profile with other dynamic profiles and figure out how to do that in an optimal way. And one of the ways that we can also help a lot is by basically using storage. Okay, so that's going to be the way we can address this problem of dynamics. So one of the good things is that battery costs are coming down. So here's a graph that was actually created by a former graduate from BYU, Wes Cole, who then did his PhD at University of Texas, one of my students who's now at NREL. And basically you can see now that as we're here 2020, and you can see what the forecasts are with, again, lithium ion systems, so it's existing technology. So these are like 3 projections, and again, you don't know exactly how it's going to work out, but this is like the high level cost in terms of how it goes down, mid, and then low. But you can see, let's just take the mid as the average. So we're going from like a number 370 down to 150 over that period of time. So half the price of storage. So storage is now starting to be adopted, used a lot, the electrical storage around power plants, and so we're going to start seeing a lot more of that in the future. And again, because the price is going to be going down, it's going to be more attractive in the future. Of course, we can keep working on research on batteries and electrical energy storage, and again, some of you in the audience may be actually working on things like this, but there's a lot of room here for new materials, new anodes, cathodes, and so on, better understanding what's going on, new materials that we can use, and how we sort of understand how they operate and avoid having fires in your laptop computer and things like that. So there's a lot of research that needs to be done here, and this will all can be done toward the future, because again, what I showed you, those prices are for current lithium ion technology that are going to go down. So now let me move over to a slightly different topic, which is an older idea, which is thermal energy storage. So the idea here is pretty simple, which is that if I can heat up something at the right time of day or cool it down and save it, store it, then I might be able to use it at a different time of day in order to meet this variable demand that I've got to worry about. And so this will actually allow me to reduce the cost of the equipment I'm going to use in the end, reduce maintenance costs, reduce energy costs, and so on. And so I can play this game of, okay, does power cost less at night than it does during the day? Then maybe I'll use essentially the nighttime to essentially store energy and then bring it back the next day. So that's the whole idea here. It's purely an economic value proposition. So there's a number of things already out there that are already being used quite a bit. One kind would be to use steam, or you could use just chill water, or you can make ice at night and then basically let the ice essentially warm up and then be able to use it as cold water later. So for air conditioning probably. So a lot of what we worry about in Texas is air conditioning, and maybe you don't have quite as many demands on air conditioning, but I'm sure you have some. So at the University of Texas, here's a parking garage, like 5 stories. Okay, that's a thermal storage tank. Okay, big size. Okay, University of Texas operates a microgrid for its power. It's basically disconnected from the Austin power and also from the state of Texas power, although in emergency they could get to it, but they operate solely as a microgrid, which means they're independent of all the other grids. It's 100 megawatts. It's the largest microgrid in the U.S. So, and I'll have to remind you, we always do things bigger in Texas, right? So here's the thermal storage thing, pretty big, okay? So we're gonna, we could use this, and we're gonna use it for chill water. There's lots of ways you can do it, and so it's a simple idea. It's just simple, either heat something up or cool it down. Like I said, lots of variations we can use, and so again, it's not complicated technology, at least from the standpoint of how you go about doing it. So we think it's smart because you can figure out how to use it in an optimal way. It's going to have low cost, high impact. So we like to think of this guy here as someone who's a heavy lifter. Okay, does anyone know who that is? Dolph Lundgren. Okay. Does everybody know he's a chemical engineer? Okay, so you learned something, right? Okay. I'm going to blame that slide on Cody Powell, who's a faculty member at University of Utah, by the way, who's a former student too. Okay, so here's a simple idea about how we could use thermal energy storage just in a normal operating of a building or something like that. So here you see the typical energy requirements as we go through a 24-hour cycle. Nighttime, things are pretty low, no one's there. And then starting around 6 a.m., people start showing up, so we got to turn on essentially lighting. This will be the air conditioning down here, lighting, this is just running electrical equipment, lighting, fans, pumps. All these things are going to take energy, and you see we get a peak that's going to form here in terms of how the building's going to use energy consumption, which again mirrors the peak that I showed you earlier. But if I could at night essentially store energy, keep basically drawing almost a constant level, that I could store it here, I could store it there, and then basically bring it back and use it in order to flatten this overall demand profile, okay? So that would be one way of using thermal energy storage in order to solve an important problem. And again, if I'm interested in paying lower utility rates, I could certainly achieve that by using this kind of simple operating strategy. So I mentioned to you this is the CHP plant at UT Austin. And so it's a general diagram. I'm not going to get into detail, except again, it's like a bunch of buildings, a bunch of chilling stations, a bunch of chillers, and then natural gas boilers, turbine, combined cycle turbine plant, and so on. And it also is going to have thermal energy storage. So it's a big system, a lot of complications here that we have to keep track of, because again, if you don't essentially satisfy people in terms of providing air conditioning on a hot day, then you're going to be out of business pretty soon or looking for a new job. So here's a little simpler diagram that you think about it. So there's actually in this microgrid, we've got essentially a bunch of buildings, but then we have a number of different chilling stations that are scattered around in different parts of the campus. And here we got the thermal storage over here. And so one of the things that we have to worry about is, well, each one of these chillers, as the campus expanded and added more power requirements and so on, or heating and cooling requirements, Then they'd add maybe a chiller from time to time. It would be a different chiller than the one they had before. So you have these sort of, mixed systems here where they have maybe 4 different kinds of chillers that they're operating, and they have different efficiencies. So we wanted to look at this, and so actually, I mentioned Cody Powell. So when he was a graduate student, he had this idea that let's go to the power people and tell them how to run their system more efficiently. And so got together a bunch of other grad students and undergrad students, and basically went about analyzing the whole system and figuring out how we could do that. So here's a product of that work. So again, you've got this cooling load, you've got 4 different chillers, and the whole goal is to make chilled water, but do it in the most efficient way and also at the right time in order to make this whole system work and then essentially save money. So again, chillers are pretty straightforward. It's just going to cool the water for air conditioning, and we got other power requirements there, but they're less important. And the chillers are going to be different in terms of capacity and efficiency. And so trying to figure out how you optimize all that is what we wanted to do. And of course, using thermal energy storage as part of that was essentially a part of, also another step that we wanted to carry out. So here is a way it kind of works out. When we started off, this is like the operator version of it. And so each color here means a different chiller is going to operate. So chiller 4 is the biggest one, and you can see it's going to be operating all the time, 24 hours a day. Chiller 3 is the next one, the orange one. It's going to be operated only between 8 and 6 p.m. as kind of a help to the air conditioning. Then we've got this chiller number 2 here that was being operated starting around 10 in the morning to 8 o'clock at night. Again, kind of matching the load. Here's the load profile right there. And then the last one's going to be chiller number 1, which is going to be use some at night and also some during the day. But the point is that this was just basically kind of how they operated it. They didn't necessarily do a rigorous analysis of it. And so we decided we could do that. And we didn't really have to use load forecasting in the beginning. That was, they were using chiller 3, which is the orange one, is the least efficient of those chillers. And you'd like to figure out a way not to do that if you can by using thermal storage in some way. So case B that I'm showing over here means, okay, I'm going to forecast the load ahead of time, 1 day ahead of time, based on what we think the weather is saying, and use optimization, and then figure out, okay, what's the most efficient chiller. And by doing that, we're now able to still meet the demand, as you see here, okay, but we were able to take this chiller out of service and not even use it at all. Okay, then if we say, let's bring in thermal storage, then we get to this case, which is, okay, here's the load again. We've got essentially chiller 4 and essentially chiller 1, it looks like, okay. And then you can see here's the load profile, but then in these areas here, we're doing thermal storage. We're sending that to storage and then basically using that to hit the peak, okay. You might say, okay, great, that was a nice little study you did. Did you save any money? Well, yes, you do, because here you see 3 cases. So what they were using, which was arguably an optimal policy called equal ratio chiller loading that a lot of manufacturers recommend. But then if we go in and analyze, do modeling of the system and so on, and do either static or dynamic, you can see we can start reducing the cost, in this case, $23,600 to $21,800. These are now daily costs, okay? So if we could then go from here to here, save, $4,000 a day, it's $1 million. So it's not, anything trivial that you could do. And then if you start thinking about, okay, what about time of use pricing, then we can get, even numbers like 17% savings. So I think the university looked at that and said, well, we like saving money, and so we'd like to do that, and this will be a more efficient system. You can also say, okay, how do we operate the bigger system now with all the power plant components in here? That becomes a much bigger kind of optimization problem. And you can see again, here's another flow chart that shows you all the kind of important components. There was interest at some point a few years ago of saying, let me show you this, that in Texas, because it's a competitive market, sometimes there are shortages of power. And here you see that the price, because there's a shortage of power at 4 o'clock in the afternoon in the summer, that was August 29th of 2011, that the price went from the normal 2 or 3 or 4 cents per kilowatt hour up to $2.50. Well, that's what they're going to charge people who draw power then, because That's what the people who are providing the power say it's going to cost. You have to bring a lot of things out of service in order to meet that demand. So the university said, well, maybe if we could then sell power back to the grid and hit these kind of peaks, we could really clean up, right? Well, turns out that if you don't predict the peaks ahead of time, then you don't clean up, you might lose money, okay? But we did that analysis too to make sure that, things would work out. And so again, it was a big optimization problem, which I'm not going to get into. We're using nonlinear programming to solve the problem, but now we're starting to worry about, how we run the turbine systems and so on, as well as the thermal storage. And so it's a big optimization problem that a couple of students worked on. Okay, well, let me go to the end here and talk about concentrated solar power. So that's an alternative to photovoltaic, where now we're going to essentially use heat from the sun, and we have essentially a carrier fluid that's going to go through these parabolic collectors that are basically going to have reflectors on them so that they heat up this carrier fluid, and basically it goes in here to a steam turbine. We can make steam that way and then basically go through a turbine, generate electricity. And then we're also going to have in this system, though, thermal storage, like I described earlier, in order to give us an additional degree of freedom in order to benefit the system. So you're going to concentrate sunlight to heat the fluid and then run a generator, but the question is going to be, well, how effective will that be when we know that, let me just go to this one and I'll come back. So this might be a typical solar insolation profile during the day, and this was actually, I think, not in Nevada or maybe even Utah, which might have a much more uniform thing, but more in West Texas. You got clouds rolling in and so on. You can see it's kind of a stochastic signal. It's not like a constant number, okay? It's going to vary, from hour to hour, and how can you deal with that or capitalize with it? So we did basically a bunch of, so here would be like the control system. So again, here's the parabolic collectors over here. They're going to go into essentially a temperature control valve, and this was actually a combination of feed-forward control and feedback control, but it wasn't really multivariable control or anything super advanced. They're going to measure essentially the irradiance. We could also build in weather forecasts to this if we wanted to in order to look beyond one day. You're going to take that hot fluid, put it in a hot tank, and then use some of it in a boiler in order to generate steam. But then, because we've got that stochastic variation, I've got to now add essentially some supplemental fuel, and that's going to be this red dashed line here, which is natural gas. So you can see we're going to add that to supplement it. And of course, if we're trying to figure out how to minimize the carbon emissions and maximize the efficiency of the system, we'd like for this to be zero if we could, but again, as you'll see, it's not possible. And of course, at night, I've got to have natural gas, right? So I can't run the system, at night if I'm relying on solar energy. So that's where the energy storage comes into play. I could then draw upon that energy storage as a way of essentially preempting, what I might have to do with natural gas. So those are all the trade-offs that we'd have to worry about. So it turned out that the modeling was not too complicated. As chemical engineers, you know how to model tanks. You can do the mass balance and the energy balance. I'm not going to go into this in great detail. It's in papers we've written. And then that parabolic collector, it's a distributed parameter system because as the fluid moves through there, it's going to get heated up progressively as a function of distance. And so, we can model that. We can model the boiler pretty easily. So these are not what I consider to be complicated models that required a lot of horsepower computationally. So there's that picture again. So what happens when you start going in and try to optimize the system? And we'll start off without storage to see how well we can do without storage. So this is what would happen if you just relied on the sun during the day. And this is not necessarily starting at midnight, but rather more like 6 a.m. in the morning. So you can see again, we get this solar profile, the available solar, that's the blue line here. And then essentially what we actually are able to collect is essentially this red line. And how much natural gas do we need to use? Well, as long as we've got solar coming into the system, we don't have to use any natural gas. But then just before the end of this, as this tailing off, we got to start ramping up. And then we've got to run natural gas starting here about hour number 13. And we have to run that all the way through the night and then back into the morning again. So that would be the worst case that we'd have to worry about. So then we say, okay, let's bring in a system with storage and power. And so now you can see that we've been able to extend this period right here now to like 17 hours basically. Again, on a sunny day, I should point that out. So the first case was sunny day, this is a sunny day. And we're able to collect most of the solar, but not all of it. But the point is that we're actually able to decrease considerably the amount of energy that's required with the natural gas. But then when we get clouds, then all of a sudden things go very badly. Okay, as you can see here, you can see that profile of solar has now changed a lot. And this again was sort of uniformly cloudy. In other words, it's not like clouds come, they go away again. It's really more clouds than not. And so you can see now that it's really hard to run the system because of these stochastic variations. That means the natural gas has got to keep coming in, bouncing up and down, trying to, because the whole goal here is to come up with a constant load. You want to operate a constant load in the power plant, generating power. And so you can see again how much natural gas you're going to use if you operate that way. And then if we add storage, that was with no storage, we do a little bit better, but I would not say this is a great improvement. It is an improvement. So we're able to, again, use less natural gas, but we still got the same problem of, okay, we're just not getting enough energy from the sun. I suppose we could add more parabolic collectors in that case in order to get more energy in, but again, that costs money. So if you again get to the end here and say, let's summarize, what the results are. Here are some percentages that you might get, and just look at down here. It's really the key thing to look at is this supplemental fuel requirement. So you can see, sunny day, no storage, 12.5 or 12.6. Sunny day with storage, 7.1. So there's where the big decrease is. But if I have a cloudy day, I don't really get the benefits. Now you could redesign the system, recognizing, okay, I'm dealing with cloudy days. You probably wouldn't want to run the system where there are a lot of clouds anyway. I was told yesterday that Utah is actually very clear, so maybe you could do this in Utah successfully when the sun's out. But in any event, it is an idea, and again, redesign. And so there are a few of these kinds of plants that have been developed out in California and Nevada, some in Europe and so on. So it is a direction that people can go. I'm going to go ahead, since we're running short of time, but that's sort of thermal storage. But now people are talking about district energy storage. So now instead of having just one facility using storage, thermal storage, now we can talk about a network of homes, again with thermal collectors up here on the roofs, and then basically seasonal storage, sticking it underground and then bringing it back up again. So there's a lot of things we can do to improve the performance of these systems in order to reduce energy use. And these graphs actually show it, I think, pretty well, that this was like a bunch of houses. So this is not a plant or anything, but rather a power plant, but it's really just a bunch of homes up in Canada. And so you can see again, how can we improve this? Well, the blue bar here is essentially what happens with space heating requirements. But once we implement the system, then you can see the space heating requirements are a lot smaller. So we're able to save that much energy right there in the gold bar there. So that's going to be stuff that is obtained through solar. So again, these are all things that we can start thinking about for the future in order to reduce energy use. In the future, I think that this is also going to go into the chemical plants and refineries and so on, that there's going to be an increased focus on where energy is measured, on its usage in every plant at every place. That doesn't happen currently. You sometimes don't find out until weeks later how much energy was used. Trying to reduce carbon footprint is important, and being able to interface with smart grids, as I indicated earlier, and then figuring out clever ways to bring in renewable energy. That's going to be the slower part of this, but certainly energy storage can be part of that too. So let me skip that and just go to the conclusions here. So there are certainly many opportunities how we can improve energy efficiency, not only in your own personal homes, but also in buildings, office buildings, in refineries, chemical plants, factories, and so on. And if I know that the topic of sustainability is kind of hard to discuss because it can get into all kinds of issues around waste and other things. But certainly if we use energy efficiency as a surrogate for sustainability and the carbon footprint, then that is, I think, a good single objective function that we can think about. We can make design changes, we make operational changes in order to achieve that. Bringing in cogeneration, smart grids will also be a big benefit. And then finally, the idea that energy storage and using control strategies will be critical technologies in order to deal with the dynamic environment that we're facing in the future. Okay, with that, I'm going to stop, and again, thank you very much for your attention.